Okay, so today I'm going to be explaining what I worked on in the power distribution board, part of the solar car team. So the first thing I want to look at is the power path ICs, and what this does is that part of the solar car relies on the DC-DC voltage, and another part of the solar car relies on the voltage from our auxiliary battery pack. Okay, but when one of these fail during the race, we don't want half the components in our car to not function. So what this power path does is it checks um, if um, these voltage supplies are valid and selects from them as V battery for the rest of the sources, for the rest of the components, sorry. Uh, Now you might be wondering, how does it select if it's valid or not? Well, it does this with under voltage and over voltage checks. So V1 is valid if it is under a voltage specified by the voltage over here, given by the voltage divider equation, and same thing with over voltage. So if it's over the voltage specified here, then it's valid. Same thing for DC-DC. Um, and basically, if the auxiliary is valid, then we just use V1 and we don't use V2. But if V1 fails, then we use V2 as our V out. So you might be also wondering, how does it select the power path electrically? Now it does this using two back-to-back PFETs, and the way it works is when, let's say, V1 is valid, um, the the gate discharges current through G1, and the resistor basically limits this current going to G1, uh, so we can turn the PFET on slowly, and we can prevent voltage fluctuations and current inrush. Um, and the opposite is true as well. When we want to turn the PFET off, we supply voltage to the gates relative to the source. So it goes through this diode, which acts as a short, so we can turn off the voltage supply pretty quickly that way. And you might be wondering what this capacitor for. This capacitor and this resistor, along with this uh, capacitor at the output, um, they're used to determine uh, like the inrush current, and their values are determined by the system of equations over here. And there's a lot of givens in the datasheet that help you determine this. So TG switchover is given the datasheet. We just need to know our I load, which comes from these supplies, and etc. Um, you might also be wondering how the rest of the components were selected. And the rest of the components were selected just using standard values in the datasheet. So for example, this decoupling capacitor, sorry, were selected based on the datasheet. And the resistor pulled to ground over here, for example, which just disables hysteresis. Um, Same thing with the capacitors over here. Uh, these are just bulk capacitors selected as well. Um, and enable and shutdown are also connected to they let firmware enable the IC or shut it down, and when it shuts down, these V1 and V2, the over voltage and under voltage timers all reset. So it basically resets the chip. And valid 1 and valid 2 just invalidate V1 or V2 by firmware. So they pull the line low, so we need a 10K pull up to 3 volt 3 so the line isn't floating. Now, this is one power path IC. There's another very similar power path IC over here as well. And this does the same exact thing, except um, it V out over here, or V battery, is connected to um, the DC-DC, the components that use the DC-DC. And if the components that use the DC-DC no longer have the supply, then it just switches to auxiliary. So it just switches the priority for the rest of the components, and it's the same IC. Uh, we also have you might also be wondering why we don't have a TVS diode and a filtering capacitor on this voltage line, and we actually do, and it's over here. Um, so we have a TVS diode for electrostatic discharge protection, and the filtering capacitor, which is pretty large. Um, and also, please mind that this DC current sense is wrong. This should have been connected to this resistor, and it just amplifies the, the voltage difference to tell us what the current is at the output, and then firmware can read it. It was done wrong on the schematic. We also have a DC-DC voltage sense. What else do we have in this project? We have a hierarchical schematic. So over here, with a bunch of load switches for the different components. So if you look in the project panel, we have a camera, we have steering, we have display, spares, front light, fan, etc. And all of these just use this hierarchical schematic. So for example, DC-DC 12 volt is VCC for load switch 1, solar sense 1 enable 0. So if we go over here, it might make a bit more sense. So, um, for example, pedal enable goes to like in0, uh, and same thing with in1. This just prevents us from having to copy paste everything. And these are just load switches that let us turn everything on and off. The last thing I wanted to show you was oh, we also have temperature and current temperature sense for a couple things. But again, this one is connected wrong. For example, the thermistor should have been connected between the inverting and non-inverting input of the op amp. Last thing I wanted to show you was our UV cutoff for our battery monitoring system. So what works over here is we have a PFET and we have a fuse connected to it. This is just for protection. Um, but basically, this capacitor over here and this resistor, they slow down the on time of the capacitor, sorry, of the PFET, and this does it by increasing the gate capacitance, and then the resistor just limits inrush current. So the PFET is very slow when it turns on, and this gives us the advantage of limiting inrush current so we don't damage any of the other components, and it also prevents like very high voltage fluctuations in the middle, in the very beginning. And this is just a filtering capacitor. Um, connected to that helps fuse the aux with its regulate voltage. And over here, all we have is comparator, and it basically compares. It checks if um, the battery voltage is above 11.6 volts, which is this fused battery, and if it is, then it uses the PD 12 volts at the output, and then we use like a voltage divider so we can um, read the few battery status. Firmware reads this, and if it's good, then it just leaves the battery on. If it's not, then it turns the battery off for a little. Because if the inverting input was, uh, if the inverting input was higher than um, the battery voltage, then we know something's wrong, and then we just ground gets used at the output of the op amp, and then we know the status of the battery is probably bad, so we just turn it off. And this is just a low dropout regulator. Yeah, low dropout voltage regulator over here that just converts 12 to 10 volts. Um, Now to see the PCB, this is how it looks in 2D, and this is how it looks in 3D. We'll try that again. This is how it looks in 3D. Now I did a lot of this routing, but a lot of it has to be changed because we're switching out components and fixing mistakes like I've showed you in the DC-DC current sense and temperature sense. Also, some things are out of stock, so it needs to be replaced. So I'm going to be doing a lot more routing for this. But yeah, that's about all I had for our power distribution PCB for solar car team, and that's about everything I did. I hope you enjoyed watching. Thank you.